Good afternoon. We are going to start the second session. Here we will be speaking about variable stars, and people who want to go to the AGN notebook, I think the link is on the chat.
It is already recording, so you can start.
Okay. Okay, so good afternoon. I'm Lorena Hernández Garcia. I will be presenting this notebook for variable stars using ALeRCE. And this notebook has been done by Alejandra Muñoz Arancibia, who is also in this chat, and we will be helping with questions. And well, none of us are experts on variable stars, so we invited Marcio Catalan to be here also in case there are more scientific questions. And also Ernesto Castillo is here in case there are any questions about infrastructure. So you can put your questions in the chat, or if you need to stop me, go on. And I hope we will have some time for questions at the end. So the link for the notebook is in the chat in case you want to run it at the same time that I will be explaining. And I will go a little bit fast because there are many things that I want to show you. So in case you want to have more information about anything, just let me know or stop me, or wait until the end. So first of all, these are the requirements. So we need to import typical Python packages, and then there are these commented commands that you need to run before start. Well, the first time that you go into Google Colab. So I already ran the notebook because my internet is not that fast. But well, PsychoPG is already in Google Colab, but also for P4J, which is to estimate the periodogram. And you have to do the same with the ALeRCE client. You have to install it at the beginning. And once you have installed everything and have import all, you can connect to ALeRCE and start doing some science. So this is the table of content of the notebook. It starts with an introduction also to the classifiers and taxonomies used in ALeRCE, and then we do different things. The first one is to carry one variable star and plot its light curve, correct it from extinction, estimate the period, and also show the counterparts from Sinbad and animate from Aladdin. And then we do carries of sample of targets, and we will show 3 different examples. One using a small sample of stars from the ALeRCE client, another one with a larger sample of stars, also using the client, and the last part will be by using the database to carry a larger sample of stars. So at the beginning, there is some introduction about what ALeRCE is and what ALeRCE does. And well, you have seen this figure during the tutorial. So you know that ALeRCE classifies sources into up to 15 classes. And well, these are the taxonomies. Depending on the stamp classifier, we have 5 different classes. And using the light curve classifier, when we have more than 6 detections, we can classify in 15 subclasses. And in particular, in the case of variable stars, we can differentiate between these ones, which are long period variables, ALeRCE, fates, eclipsing binaries, delta Scuti, and other periodic variable stars, which are these ones. This is the confusion matrix from the paper of Paula, and this is the part related to stars. And well, now we can start carrying data from ALeRCE. So we will start by carrying one target. And for the example, we have selected an ALeRCE from the Catalina survey. The name is this one, and this is the location of the star. So this is a well-known star that has been already studied. For example, Drake and collaborators analyzed the Catalina survey, and they have already derived the physical properties of the star. So these are here from their work, and well, the star can also be accessed through ALeRCE. So I have it open here because my connection. So in the website, you can explore all the things. This is, for example, the light curve and the star. So we will see these things during in the notebook. So you can search the name of the star or whatever source by their position, for example, and you have all the data in the website. So now let's plot a simple light curve. So first of all, we have to define the name of the star. And then we define a function to plot the light curve, obtaining the magnitudes and the dates. But this is to obtain the difference light curve. If you remember from yesterday, the way in which CTF gets the data is that we have the science image and we have the reference image and the difference, which is the difference between these two. So in order to obtain the science light curve, which is the one we want to use, we have to take into account this relation here. This is how ALeRCE corrects the difference image to convert it to a science image. So we have the reference image and the difference image, but the difference image can be positive or negative depending on the sign. So this correction takes this into account. We are going to see it with the example. So this is what is done here. We define a plot we define a function to plot the light curve, but the science light curve. And then we obtain the data from ALeRCE with this function here. So we can obtain the stats from the stats and the detections and the time. And then we can plot our light curve. So this is the light curve from science already corrected, which is the one that you can find here. And well, the x-axis here is in MJD, but this corresponds to the green points in the G filter correspond to August 2018, and the first red points are from December 2018. And just out of curiosity, we also plotted the difference light curve. So well, you can compare both. You cannot see very well, but if you take a look to these points here, you see that when we correct them, it looks a little bit different. But now let's see an example of this, but with an LPV, which we just selected just to show it because we know that these are more necessary to correct. So this is the science light curve, but look at the difference light curve. It is very different. So this is just a reminder to use the corrected light curve. And now that we have the light curve, we can do some corrections. So here we do extinction correction. And for that, we use a dictionary that where we can obtain the attenuations due to galactic extinction. So first of all, we define the function to plot the data. And now we take into account this attenuation. And then we obtain the data from ALeRCE, but we do some modifications. You can read them here, but let's see in the function. So first, it takes some basic stats and the detections and also the coordinates. This is obtained from ALeRCE. And then it does a query to SIMBAT to cross-match our source with this database. And we obtain the extinction correction from IRSA dust. And then we plot the light curve and also the first image stamp. So we can show the result here for this source. This is the light curve again with the corrections and also the non-corrected one for comparison. And this is the stamp classifier. So, well, no, not the stamp classifier, this is the first stamp. So this is the science image, the reference image, and the difference image. Now, because these are periodic objects, what we can do is to obtain their period. And to do this, we use this package P4J, which is from Pablo Huize. And so if you want more details, you can go in his GitHub, and everything is explained in there. As you noted in the requirements, you need to install this because it's private, it's from him. So what we do here is, in the first part, we calculate the multiband period. This is interesting because it obtains the multiband periods and the individual periods from the G and R filter. So here, this is what it does, the multiband period and the other two. And note also here that there are some parameters that can be changed by the user. So if you take the notebook and want to play a little bit, maybe you can play with these values also. Then we define a function to plot the folded light curve and the periods that we obtain. And we obtain the data from ALeRCE. We get this data. And now we can plot the folded light curve and the periodogram. So now this is the same light curve, but now it's not in time, but it's in phase. So the period goes like from here to from the maximum to the maximum, for example. So this is why this is repeated. And well, I told you before that this is a well-known star. So here we have the period that we have estimated. And if we compare this with the work in Drake and collaborators, you see that this is a very similar value that they obtain. We can also use the periodogram to plot the data, but using a different period, which is in the do period function. So this is how the light curve looks if we use, instead of the period that we have estimated, the one that Drake estimated. And as I told you before, there are some values that can be changed. This one, so we also did it here. We changed a little bit the values, and this is the light curve that we obtain, with the folded light curve. So in the end, what we found is that this is a typical AB type ALeRCE, which is shown by this feature here. Is very typical from this type of stars. We can also search for a counterpart in SIMBAD. So here we have a table with all the data from SIMBAD. As if you remember, this is the name of the star. And we can also see an image from Aladdin. Let's see. Okay. So here we have the star. We can see its environment or whatever. And now that we know how to carry one target, we can start carrying different samples of targets. So we're going to see 3 different examples, these 3. So the first one is by using the client to obtain a sample of a small sample of ALeRCE. So here we use the sample of Liu and collaborators, and this is because we wanted to obtain the metallicity of the stars. You will see later why. Well, it is to estimate their distance is already here. So this sample is composed by 21 ALeRCE, and we cross-match it with the ALeRCE database, and we found that 6 of them have data in the G or R filter, but 4 of them have data in both. So this is our sample of small sample for stars, and we are going to plot this data and see the properties and estimate some things. So because we already defined the plots, or how to obtain the plot and obtain the data, we can directly plot the light curves. these 4 stars. These are the corrected light curves. Remember, these are the science ones. We can also plot the extinction corrected light curve, again with the corrected and non-corrected values, and the stamps, the first stamp for each of the stars. And also the folded light curve and the periodograms for each of them. And in this example, as I told you in the beginning, we wanted to estimate the distance by using the intensity mean magnitude relation. And for this, well, here in the notebook is explained how the distance is obtained. And in the end, we have this formula here, which relates the distance with the apparent magnitude, which is taken directly from the CPF data, I mean, from ALeRCE, and the absolute magnitude that is estimated here following work by Marcio Catalan and collaborators, which is a work in progress. So this is the way in which we estimate these magnitudes. So these are related to this seed, which is this one, which is related with the metallicity of the star. This is why we selected this source to do this study. And the magnitude in R is also related to the period that we already estimated. So in this part here, we estimate all these magnitudes. And here we also calculate the colors, the mean and the maximum colors. So in the next step, we put all together just to have it, let's say, organized. And then here what we do is to define a general function to plot different properties of wherever. So we will use this plot in the following for different things. I will remind you. And I said that here we organized all the physical parameters that we obtained. So in this table, we have all these physical parameters in a pandas format, and then we can plot different properties from there. Here, for example, we plot the distance from the R band and the one from the G band. So you see that it's a good agreement between both of them. And now we can also, well, another properties that we can plot is the magnitudes against the colors. So here we have the 4 plots. And something that we wanted to do, in particular, Alejandra and I wanted to do something related to this because it's what we remember from the university, was to compare this with a color magnitude diagram. And we found that this was done for Gaia data. So here we changed our format, which is in Sloan, to the Gaia one. So these are the relations that we use to convert our colors and magnitudes. And then we can locate our small sample of ALeRCE within this color magnitude diagram. So this yellow box is where our stars are located. So in good agreement with the location of ALeRCE. And note here also that each of these colors represent one star. So we can say that stars move like in a loop. And finally, for this example, we also can plot the period that we obtain in the individual bands against the multiband period, which you see is in very good agreement, maybe except in this point. So the next thing that we do is another example to use the ALeRCE client to carry a larger sample of ALeRCE. As you see, we are using this type of star through the notebook, but you can select any of the different classifications given in ALeRCE. So in this example, we wanted to obtain a sample of 100 targets that were detected after the 100 days after the CTF started. This is because we didn't want to have problems with the reference images, and we wanted them to be classified from the Lightcurve classifier that are ALeRCE with a probability larger than 0.9, and we want to organize them by the probability with the higher probabilities first. So in this table we have the data. Note that this is the head, so it only appears in the first 5 sources, but we have here all the information for the 100 targets. In the table there are all the different values, but if you want to list all of them, you can do like this, and here you will have all the information that you need in case you want to do some histograms or plots. And this is in fact what we do next. We plot here the maximum color for the sample and the number of detections for the sources. And then using the function that we define to plot different values of the stars, this plot properties, here we plot the maximum color against the mean color. And you see that all the sources are located here, and this is related to this loop that I was showing before in the Gaia plot. So we can also do the plot of random sources from this sample. So here we have data for 3 of them. Here's the size. So these are the properties and the folded light curve and the periodograms for the 3 of them. And then we wanted to do something which is interesting for variable stars, which is to plot the light curve, the amplitude versus the period from the light curve. But we noted that sometimes the folded light curves are like this. So there are some points that are not from the light curve, and if we want to estimate the amplitude, this might we can have errors with this. So what we did to avoid this was to estimate the percentile, the 5th and the 95th percent of percentile for each of the filters. So here in red, this is the 5th percentile and the 95th, and also for the G band. So points above and below these points are not used to estimate the amplitude for both the green and the red. Okay, so we do this, and then we can do this for the whole sample. Well, here we obtain the multiband period that in this case is not estimated is not calculated using the P4J, but this is a feature obtained in the features table from ALeRCE. So in this case, we obtain this directly, so it takes less time. And here we can obtain the amplitude for all the light curves using this technique of the 5th and 95%. But here is a warning that this might take some time, so do it just in case you need to do it. And in the end, we can plot the amplitude against the multiband period. So here you see that most of the sources are located around minus 0.25 or so, which is a period of about 0.5 days. And this corresponds to AB type ALeRCE, and from here to the below this point, it corresponds to C type ALeRCE. We will see this a little bit later also. And so the last example that we want to show you is to use the ALeRCE database to carry a sample of ALeRCE. And this is useful when you want a very large sample of sources. In case you want, I don't know, like 100 or 200, you can use the client. But if you want to carry more sources, it is better to connect to the database. So this is the first thing that we do, is to connect to the database. And in the database, there are many tables. So the first thing that we can do is to see what are the different tables. So these are all of them. And here we put some explanation of the most important tables. And well, you see that there are from WISE, there are detections, from Gaia, from stats. There are many different tables that maybe you need some time to take a look to all of them. But what we do here is to obtain, sorry, I need to go in the beginning. Okay, now we can see what are all the tables and with all of their columns, and this is the data type that you will find. So for example, in the WISE table, you have all the different filters and data quality. You have the detections. So here, for example, you have the magnitudes. Well, there are all of these tables. So you can go and see what is in each of the tables and see what is the one that you want to use for your science case. And well, I think this has already been explained, but if we want to ask for candidates, it is important to understand how the probability table works, because here we can do a query using SQL to obtain all the ALeRCE with a probability larger than 0.7. But what we obtain is that we get long table with this is the number of rows that we obtain. So if you go and see this, you see that there are many rows corresponding to the same ID. But if you go in the class name, you will see that this corresponds to the different probabilities assigned to the same source. So well, this is what we did here. This is that we obtain all the classifications for the same source. So if you count, there are 15 here. So one thing that can be done to avoid this is to merge the probabilities and obtain only one row per source. So here we have all the probabilities for each of the classes. So this can be done for the whole sample, but we have commented this. It is commented here because this will take long time, very long time. So you have to do it just in case you need to do that. But there's an easier way to obtain just one not one row, but just one line, and is to use the ranking. So in case the ranking gives you with what is the class that suits better the source. So here, for example, if we want to obtain an histogram from the probabilities of these sources to be ALeRCE, that we said that we wanted them to be larger than 0.7, we can just add the ranking and the class, and this will give us one row per source. I mean, the source will count only once. And here we can check how many stars we obtain, and this is about 16,000. So it's a huge number. And then we can use again this function that we defined before to plot some properties. So in this case, for example, we plotted the difference between the first and the last stamp against the number of detections. And the last thing is that we carried and to do a query from the features table. So this is because we wanted to follow the same example as before and to do a plot of the amplitude versus the multiband period. So, but we need to do this quickly because this is a large sample, and obtaining the amplitude the way we did before is very time consuming. So let's see how we do this. So here from the feature table, we can obtain the mean variance and the multiband period. The mean variance is a feature that is related to the amplitude, and in fact, it is corrected for these points that doesn't suit well the amplitude. So so this is an example of a few sources. So we have the mean variance and the multiband period for each of them. And then we can plot this data. So here you see that there are like two different subsamples differentiated like here. So we can compare this with the work in Sanchez Saenz and collaborator, the work by Paula. Here, this is obtained for the whole sample, and so this amplitude versus multiband period is able to locate differently the AB type ALeRCE and the C type. If you take a look here, I don't know if you can see it very well, but this is the part corresponding to AB type stars, and this is the part for C type. So if you took a look to the confusion matrix before, you will see that ALeRCE do have some errors, and this is because these type C ALeRCE are less, and also sometimes they are confused with other types like eclipsing binaries that have a smaller period. So the last thing that we do in the notebook is to plot different light curves for one for an AB type source and another one for a C type. So here what we do is to select from the periodogram, because we know that these are differentiated by their variability time scale or their period. So we define here one with a period of minus 0.25 and another one with minus 0.5. So at the end, we can plot this light curve. So this is a typical from an AB type ALeRCE, which is very similar to the one we saw in the beginning with this feature here. And this one is typical from an C type. So you see the difference and why this amplitude versus period plot can allow to differentiate between them. And so this is the end of the notebook. At the end, you just have to close the connection. So in case there are any questions.
Thank you very much, Lorena. So far, we don't have questions in the chat. So maybe in the meantime, we can point out some things. The examples that we have shown here, for instance, for the features, included very few features. There are many more you can explore. We invite you to explore Sanchez Saenz et al. Paper, where the light curve classifier is explained in detail and also described these features in detail.
Yes, in fact, this last part, which is about the database, as I said, when I saw the tables, there are many tables and there are many features. So you need to go and explore what's in there, so you can understand and or you can ask, read the papers or wherever there's all the documentation, and we're open to answer any questions. You can email anyone from ALeRCE here.
So we don't have questions yet.
Or if someone needs to or wants to see in more detail any part of the notebook, just let me know and we can see it in more detail, because I know I went a little bit fast because I wanted to show you everything.
Yes, also several things were also mentioned in more detail by Francisco in the Supernova notebook. We made analogous to that case, but there are many more things that you can do for variable stars. Also, we encourage you to apply your ideas in the next hands-on session.
In fact, the next part of the tutorial, which is the last one, it's going to be about hands-on session. So I encourage you to take a look to your science case or to your favorite notebook and run it, and maybe you can search for your favorite source to check if it is in ALeRCE, or you can modify the notebooks and do your own science. There are many things that can be done.
Okay, I don't know if Marcio or Ernesto, do you want to mention something more about this session?
I only want to remark that there are about 8 minutes left until the end of this session. So I enable if anyone want to ask directly by his or her microphone. So I don't know if.
Yes, that would be good to hear someone.
Yeah, I can probably add that the examples in this notebook focus mostly on the ALeRCE stars, as you have seen. There is, of course, the possibility of extending that to the taxonomy that's currently covered by ALeRCE. At the same time, it's a somewhat limited taxonomy. We are aware of that as far as variable stars go. But our plan for the future is to extend the taxonomy so that more science cases involved in different types of variable stars can be properly covered.
We have a question in the chat. Alvaro asks, are the classifications done by using the ReDNet light curves?
I think Marcio could answer this question better.
Right. So Alvaro, no, the classifications are not done using the ReDNet light curves, although color information is used whenever available. So also position in the galaxy is typically a feature that is used to separate, for instance, an extragalactic object from a galactic one. So it's not used directly as such, but it's kind of convolved into the positional information that's used by the classifiers.
Hello, can you hear me?
Yes, Alvaro, I can hear you.
I want to comment because I was wondering how the high ReDNet sources may impact in the accuracy of the classification. Have you explored that in any way?
Yes, I'm not the best person to comment on the classification itself, so I don't know if there is anyone connected who would like to comment on that.
The indicated person is actually given the parallel tutorial, who is Paula Sanchez-Saez. So I would guess that it is more explained in more detail in her paper, but we can ask her and also answer by email.
But anyway, I think it's because the information about the color is not given by CTF, so it is difficult to correct from that.
Oh, okay, perfect.
Yes, also in the heavily reddened regions, sometimes we do not have the source detected in both passbands. So in the bluer band, the object may be extremely faint, so barely detectable, and it may be more easily detected in the red band.
Okay, we have another question in the chat. Rodrigo asks, what kind of features do you use to separate binaries from RRC?
Marcio, can you answer this one?
Yes, this is again the million-dollar question, right? How to separate binaries from RRC. So at present, the classification for binary stars is not done in great detail. Basically, the binaries are included as a sort of umbrella class for the different subtypes of eclipsing binaries, whereas the C-type ALeRCE are included as a subtype of the ALeRCE stars. As you can see here in the taxonomy, we just have the ALeRCE stars as such in the confusion matrix without the separation between the C types and the AB types. And we do suffer from the usual degeneracy when we try to untangle C-type ALeRCE stars from eclipsing binaries, that it's extremely hard to do that without additional information, including, for instance, colors, and also positional information that sometimes can help distinguish between a fewed eclipsing binary that's in the plane of the galaxy versus a halo ALeRCE stars, which is where the C-type ALeRCE are most commonly found. So the short answer is we do not have the final solution to this problem. It's still, as you know, Rodrigo, an open problem in the literature.
Also related, Carlos asks in the chat, is there any kind of issue to detect the right period of eclipsing binaries? Is there a confusion between the correct or the half of the period?
Yes, that's a great question. And this is a problem that we've had consistently faced. So we are often affected by the confusion between the presence of twice the period or half the period being the correct one. So we are currently implementing algorithms to solve this problem. And one of them is to check if within a given phase for the period, a given cycle for the period that we are calculating, if there are two minima as opposed to just one. And if there are two minima, then we probably know, and if this was classified as an eclipsing binary, then we probably know that the period is correct. So this is one approach that we are looking into, to basically count the number of minima for the reported period and to see if it's consistent with the eclipsing binary classification. Of course, we have to do it quickly enough that not much time is spent on any given object, as otherwise we are not able to fulfill the requirements of an alert broker such as ALeRCE that needs to process things very quickly. But it's basically like 1 second per star at most.
Carlos also adds, but if you hit the twice of a period for a pulsating, how do you make the difference?
Well, the pulsating star should have just one minimum. So if it's classified as for instance, as an AB type or ALeRCE star, and you multiply by 2 the period, and you find 2 minima, then you know that the classification should be with the other period, right? Not with the period multiplied by 2. That would be consistent with the ALeRCE star. For the eclipsing binary, on the other hand, you'd need to have 2 minima, unless, of course, it could happen in the case of a detached system that you could have one minimum that's basically imperceptible, but that's a risk we have to take. Does that answer your question, Carlos?
Here Carlos says, So you make first the classification, and with the classification in hand, you identify the correct period?
Right. So that's the approach we are looking into right now. With the classification in hand, we make this additional check to see, for instance, in the case of the EB, the eclipsing binary, if it has two minima, as it should. But yeah, it should be consistent with the classification and the period. Because the main problem we are facing right now, and this also from Rodrigo's question, right, when we examine our results with results from other papers and from the literature, is that we are very often getting the periods or the eclipsing binaries incorrectly. We're getting them wrong by a factor of 2. So this is the main issue we are trying to fix right now. So if the star is classified as an eclipsing binary, does it have two minima as it should? If it doesn't, then the period has to change. And that's what we are looking into, as I said.
We have 2 more questions, and we are running a little ahead of time. So we can continue by chat or as you prefer.
Sure, Carla.
We have 2 questions. Rodrigo asked again, can you say something about the contamination of your classes?
Yes, Alejandra, I think I already answered that as part of my last question.
Okay.
And also Carlos's question. There's Carolina Sensano's question. Yes. So Carolina is asking about the ALeRCE with the Blaschko effect. I don't know, Alejandra, do you want to read the question?
What about ALeRCE with the Blaschko effect? Have you encountered them? Maybe have problems in the classification because of them, or the irregularities are far enough in time that you cannot see them?
Right, Carolina. So yes, of course, there are Blaschko effect, stars affected by the Blaschko effect all over the place. And indeed, when you have the Blaschko effect, for those who don't know, it's a long-term modulation of the main pulsation cycle over long periods of time. So this modulation, which brings about additional scatter in the light curves, does make it more difficult for us to properly identify and classify these stars because we have more noise. So currently we are not studying the Blaschko ALeRCE stars separately from the other ALeRCE stars, but this is work in progress. We do want to do that when the final taxonomy is implemented so that we can correctly assign the Blaschko ALeRCE stars and the non-Blaschko ALeRCE stars to separate subtypes, so to say. But yes, this does make it harder because of the extra noise that's brought about, and particularly when we don't have sufficient time coverage, which is typically the case here, that we have beautiful complete light curves with the modulation period very well monitored and covered, then it's hard to tell the extra scatter from just something else other than the Blaschko effect.
Okay, so I think we should stop here and go to the break before the hands-on session. Thank you very much for all the attendance. And Ernesto, do you want to mention something about the next session?
Well, there is going to be 3 short exercises in order to query them, use the API and plot some scenes. So I encourage you to go to the next sessions, and we are going to split the room meeting in 2. So I encourage also to make as many questions as you want.
Okay, thank you very much, everyone, and see you at 4:15.
Thanks a lot. Bye-bye.
Thank you so much.
Bye-bye. Thank you.
Later. Bye-bye.